All right. People are getting settled in. Um, can I, for those who are on Zoom, can you like say like whether or not you're presenting in the chat so then I can know who to give screen sharing permissions to. If you're ready, like you could just say what if you're going to be presenting and which team you are on. And then for the folks that are in person, I think it'd be best if you just like kind of plug into the wall and share your screen. Also join the Zoom, but mute yourself and turn off your audio so there's not that feedback. Um, yeah, so I'm not gonna decide the order right now, but like, can I just get a show of hands of who is presenting, and so I can just jot down who's doing what. Um, yeah. So we have Plant Pulse, right? Plant Pulse. Um, what other team? Aiden, what's your team name? Jaundice detection. And then what's the other team? Enrico, passive ocean monitoring. And what other teams? Yeah, right. Oh, what's the name of your mosquitoes? Um, they could talk on the Zoom and then while you share your slides in person. Yeah. Is that everybody in person? Everyone here is on the team. Okay, cool. Yeah, I think I saw Peter is with Coral Helping Hands. Oh wait, I need to write that down. Coral. Okay. We have non-invasive imaging. Uh, electricity-free PCR thermocycler. Sounds very cool. Is that all for the online folks? Um, and then like if possible, yeah, you can also write down, or I'll take note of who's on what team so I can keep track of. Yes, cool. So in no particular order. Oh wait, who requested to go first? Like it, like or wants to go early on rather. Oh, also can I
Oh,
go first? Non-invasive imaging. Yeah. Okay. Yes. So, Shatij, can you share your screen?
Indumita would be sharing from our
sorry.
team.
I'm gonna share my screen.
Okay. Okay.
That's okay.
Let me know if you have any difficulty with that.
Okay. The thing is, we didn't have time to make a full PowerPoint, so we're just gonna share the screen and talk about the table, if that's
Yeah.
okay.
Yeah. That at the very least, like that. That's good. Yeah. Let me plug in my computer so that everyone can see person. Uh,
Can you see my screen?
can you hear me? Oh yeah. Yeah. Yeah, okay. Can you say something real quick?
Can you hear me?
I think it's because I'm plugged into HDMI now, so I need to make sure that the sound settings work. 1 second. Um, um, sound, audio. Sorry, technical difficulty. In the meantime, can you say something? And yeah,
Can you
it's
hear
hard to
me?
see if it's a false negative or true negative, actually.
Can you hear me? Hello?
Or someone on this in the in-person Zoom, can you try saying something? I'm wondering.
Wow.
Okay, yeah, it's probably not working. Okay, Zoom is very slow. Do you have permissions to share something? Share a screen.
Yeah, my share screen is working. Oh,
Okay, I think my Zoom is just crapping out. Let me just force quit it. Okay. I'm not gonna share screen right now because uh if people could just open their laptops, I think that'd be easiest. I think that's why I'm having some technical difficulties. Okay, first group again. If you can go ahead, I think it's non-invasive imaging. Go ahead and share slide your screen.
can you hear me now?
Yeah.
Is it okay?
Yeah.
Okay. Can you see my screen okay as well?
Yes.
Okay, so yeah, sorry, we didn't have time to do slides, but I'm just gonna run through an intro to start and then I'll show the table afterwards. So yeah, as the professor suggested, for the disease we were going to focus on is called river blindness. So it's a parasitic disease caused by a worm. I can't say the name, Onchocerca volvulus. And it's so first of all, it's transmitted to humans through repeated bites by infected black flies. And this is highly prevalent in places that are fast flowing rivers and streams. And that's why, as you can see on this map, the places where this disease is most severe is in places in like Africa. And there's several stages to this disease. So first of all, when the black flies bite the human, they deposit larvae into the skin. And then these larvae develop into adult worms over several months and they form nodules like lumps under the skin. And the adults can actually live quite a long, like 10 years, and they can release thousands of um, microphyllae, which are like immature worms. And these worms migrate through the skin and the eyes, causing blindness, which causes like river. That's why it's called river blindness. And then also severe itching and skin damage as well. And then this cycle just keeps going on. So black flies bite an infected person, and then they ingest the immature worms, and then they bite someone else, and then the cycle continues on. So it's kind of like a vicious cycle. So our goal was to kind of diagnose this at the stage where the person gets nodules, so the lumps under the skin. So this is like maybe after a few months once they've been infected, but that's when they first start to see some physical symptoms. And usually the way this is done is through a skin snip. And this just takes like a few millimeters of the skin where the lump is. And then they put this in saline and or distilled water, and then they look at it under a microscope. And then you can image and you can see if the worms are dead or alive after a few hours of it being in the solution. So our main goal was, can we do something before we do the skin snip to see the how severe the situation is? Because there's different treatment plans depending on whether the worm is alive or dead. Because if the worm is alive, then they have to try and surgically remove the nodule. But if the worm is dead, it's still a threat if it still stays in the body, like it causes the immune system to respond. So you need certain drugs to kill off these worms as well. So that was our goal, basically, to find out whether before we skin snip, if we can find out if these worms are alive or dead. And initially, I actually thought of, before we were focusing on this disease, I came up with a method for like deep tissue imaging, which was using ultrasound lens. So virtually creating a ultrasound lens within tissue, so you can optically image like deeper than usual because it overcomes like the scattering and absorption problems. But however, like after talking to the professor, we were like, he said he suggested this disease, then he was like, let's not stick to one piece of tech, because we might just be over engineering the situation. Like all we need to know is if the worm is alive or dead, and possibly like the density and how many there are. So we started looking into other pieces of tech. So the first one is ultrasound lens, but obviously ultrasound, it can be quite expensive, and we don't actually need to image the worms in order to see if they're alive or dead. There's other ways of doing it. So he suggested looking to methods of stiffness. So that's what the second method here is, indentation-based mechanical analyzers. I think Kamal researched this one. Would you like to talk about it? Yeah.
Yes, yes. So basically, Manu suggested that this could be actually a problem that could be tackled by looking at maybe the mechanical properties. So I just looked up, is there something modular and cheap available for looking at the mechanical properties of, since we were thinking of hand to begin with, because that's where if you take a snip and you by any chance make a dent in one of those neurons and then the finger is gone, that's the problem that you have if you have the thing on your hand. And so what we wanted to think of is a mechanical way which could possibly utilize some tech to figure out the stiffness at different parts of the body, because at the end of the day it's going to be affecting humans. So and this one of this mechanical analyzer that is based on just indentation. So if you open the paper, I think it'll be easier. I'll just walk them through the figure of the paper. So that one, right. Yep. So it basically just includes like a actuator, and that's being driven by a microcontroller, and there's a force sensor. And so you could assemble the thing that is made in sort of D panel that shows the entire thing, which has one indenter and one force sensor. And then you could place this on different parts of the skin. And what they did in this paper, so you could put this together in less than $100. And so that is the device that they made. And they actually, as a proof of principle in this paper, which is also highlighted in the title, they looked at different parts of the wrist, different parts of the arm. So you can see one is the forearm, the other is the wrist, and posterior, anterior, and they just looked at the mechanical properties, including differences between sexes and people of different ages. If you go through the next few figures, I mean, you don't have to open it, but yeah, there's also old people versus young people, and then you can find out what the differences are. So basically, this looks like one of those prototypes that could possibly work if we were to just measure the stiffness of the place where the worms are. And depending on how Indu just mentioned that there's a life cycle, there will be larvae and there'll be some movement, and based on the number of worms, you could find differences, and that's the hunch that we have. It's not something that has been tested for worms, of course. That's the least we could do, but it would be worth investigating given the kind of problem. If you're just looking at stiffness, I think putting something together in less than $100, one could scale it up and make it even more cheaper, and then we could think about parts that could become more modular and measure something else. But just measuring the sheer modulus might give us that in, but we are not sure whether the technology will definitely work or not. And on the mechanical properties side, there was also ultrasound elastography. The only problem being it's based on ultrasound again, and as she discussed, Indu just now, that ultrasound is a expensive tech. It's not very accessible, and the one that is able to do the elastography measurements, even like a refurbished one, would cost upwards of tens of thousands of dollars. So it's not very accessible, given the fact that it's mostly prevalent in African nations, which are not very financially well off to do with to begin with. So I mean, you can't imagine like a random clinic having an ultrasound elastography machine in Africa. And so that's out of the picture, I guess, because of that. And the other thing is electrical impedance, which was also again suggested by Indu, but there are a couple of papers that do show that you could possibly make it in less than around $50. You could make a point of care device which just measures the electrical impedance, and so resistance and impedance measurements could essentially tell you whether the skin is and I think this will require a fair bit of standardization, because as we discussed, like age, sex, many things will change this. So it's just a matter of getting that data for a wider population so that you can find where the peak for that normal curve would be, and does it differ very drastically is the question that it will boil down to when it comes to impedance measurement.
Yeah.
Would it
just
be
to interrupt, you have maybe a minute or two left. So that, yeah.
Okay.
so I think we're nearly done. I think that's the last piece of tech that we had. And with this, I think we would sort of summarize to say that resistance measurements and the mechanical properties, the indentation based analyzer, those are the two pieces of tech that we think are accessible, also cheap, easy to put them together, and will be possibly more modular and will work for different parts of your body to be able to take those measurements. So but we would like to hear thoughts, any comments people have, any ideas that people are thinking of. But yeah, I mean, these papers are all accessible on Notion. So we would also like for people to take this up. And the impedance things, the last piece of paper, the PubMed paper that is measured, it actually shows that it has been used to detect atopic dermatitis. This is a disease where you will get this big rash. It's not the smallest rash that you get for anything in general, but it's a little bigger than that, and it's an indentation that is smaller than what you see in this disease, river blindness. So it's not it's actually good that it has been tested as a proof of principle for a disease that has a lesser skin swelling as compared to what you see in river blindness, because it really swells up in river blindness. And if you look those images up, you will realize that impedance measurements might actually help.
Yeah.
That's
Great. Thank you. How about this? Since the document is on Notion,
Yeah.
for people who want to leave comments and questions, you could do that right in the document itself, maybe at the bottom or top.
yeah, you could please feel free to add comments on particular parts, just highlight them and add comment, we would know, and
Yeah.
we can.
Yeah, so that'd be super helpful if folks could do that. Just some quick feedback. I always say, like, I think y'all are going the right direction of like not constraining yourself to a certain strategy or technology. Like you acknowledge, like ultrasound is not necessarily the most accessible thing. Just to generalize that concept, it's like you're giving up information about image and space, but you're giving up information to reduce your cost to the minimal amount of information that you need to get the job done, which in this case is like, do you have the worms or not? Like, you don't need the full scope and all the information. So thinking about like what other information can I throw out to answer this question, that will help. That's one strategy or angle to shave off the cost. Yeah, thinking about the mechanical and the electrical properties is like one way to give up that is a very promising angle. But yeah, any other folks who have comments? Yeah, Daniel.
First of all, fascinating project, really interesting presentation. I don't know the tech super well, but I'm curious if there are like materials or things that you can test these like technology on beyond just like actual human skin. Like, are there gels or things you could like put an ant into and then test to see if you could detect if it's alive or not with the ultrasound or other tech? I don't know if it's gel.
I tried. Yeah, no, that's a cool idea. I tried looking it up, but I couldn't find something even in like standard material kind of things that people test a lot of substrates and with different stiffness embedded with different kind of things. I could not come up with something which was closest to say an alive worm, but it'll be super cool. I think that's the proof of principle thing that you would first need to be able to test whether you could take this to a worm, which also, by the way, extends up to a centimeter inside your body. It could be as long as a centimeter. So that's the scale that we're talking about. We would expect the mechanical properties to be different, especially in this case and in this disease because of the worm that we know of. But I mean, I don't know if that is done for insects, ants, or other organisms.
Interesting responses in the chat. Like, people are saying that people are working on it, that you could use a gel. Suitable gel that you can
Acrylamide gel. Yeah.
Which would be really
Yeah, exactly. Yeah, I think it is not a bad idea to actually start with something in lab which could be very well controlled, and then one could sort of build on it by embedding real worms, maybe starting with C. elegans, most accessible form in the lab. Yeah.
Awesome. Thank you so much, non-invasive imaging tissue team. Next up, kind of by random, but is anyone dying to go earlier rather than later? Yeah, okay. Plant Pulse, do you want to share your screen and then you can yeah, so when so one person shares screen, but then we'll take turns unmuting so that we don't have weird feedback.
I can go, yeah. Hey, so this is Plant Pulse. We are a group of 5, I believe, and yeah, I'll just dive right into the problem. You want to switch next slide?
Oh.
Yeah, so the problem we found is we think a lot of students become uninterested in plants, mostly because they kind of seem stagnant in a short time span, unlike a lot of animals that students are interested in.
Yeah, you can press like.
Huh?
Can you share your video?
Oh, sure. Yeah. Yeah, and so with that, the idea focus question is we want to create an educational activity that would demonstrate plant movement on this small time scale, which would pique student interest, kind of like it does for animals at a younger age.
So yeah, just to provide a bit of exigence, like I did by the numbers on like what the loss due to like inequities in access to STEM. And this is part of like the scope of the class, and this project is making kits that are like accessible, cheap. So I found that there are like 50 million students, and if we like do some percentages, like it comes down to about like 1.8 million STEM workers lost. And the economic loss of this, like I calculated, was like $14 trillion of like lost income. And then And there are currently like 20 million STEM workers, and with this, like an extra 2 million would be like hypothetically be like a 10% increase in innovation. And this is just broad STEM, but you know, on a smaller scale, maybe plant scientists could also contribute to this.
Yeah, so this is our FRDPARRC, looking at some specific things that we wanted to consider in our project. So, for example, looking at the orange boxes are things I thought were important to talk about. So the main goal of the project is to render otherwise invisible plant physiological parameters visible. And so we didn't want this to be some kind of number readout because we thought that that wouldn't be interesting to students, but rather some kind of visual output where they could actually see something happening in the plant, not just necessarily a graph of that. And we also wanted the results on a speedy time scale, which can be difficult with plants, but is kind of the key point of the project. Another one is that we didn't want to dissect or cut up the plants because the whole point was seeing like living plants moving in real life. And also looking at that last orange box on the right, if the device is too simple, it probably wouldn't have a wow factor. But if it was too complicated, it wouldn't necessarily be a good educational tool. And so we needed something that was a relatively simple to use technology that could show an impressive thing happening in the plants at a rapid time scale. And so looking at that green box at the bottom, something that we've decided on is a crescograph, and that's an instrument that we'll talk more about later, but you can use it to measure real-time movement in plants by amplifying the movement that the plant's making. And we thought that could be really cool because movement is, so things like growth and movement in response to light aren't things that people often associate with plants, more with animals. And it would be fun to actually show high school students or students in general that this is something that plants can do.
One of the best things about this class is getting to take real action based off of interests. And so a big interest of the group is science education. And as Megan mentioned, we hope to be able to educate high school students on the movement of plants. Depending on logistics, we might look into actually being able to educate high school students, but we'll first be building the crescograph.
Oh, there we go. Cool. So what actually is a crescograph? Cresco here, Greek or Latin, one of those old languages for growth graph. It's a growth measurement machine. So as Megan went through with in the context of our FRDPARRC, really a lot of the issues we're confronting here are issues of magnification. Plants do move, they do respond to different stimuli on a time scale that is sensible to us, but those movements are sufficiently small or too small to be visible to the naked eye. So this is an issue of magnification. How can we make those small or slow movements visible? So we can do that for example, here by dramatically magnifying those movements. This is the crescograph design from J.C. Bose in the early 20th century or so, where you're essentially just clamping a growing tip of a particular leaf here that's a kind of grass to a system of levers that amplifies that movement 10,000 times or so and renders that movement clearly visible on a sensible timescale. These dots here that are shown to the right here, those are dots on the order of a few millimeters or centimeters apart, and each dot is essentially collected a second at a time. You've amplified that motion several thousand-fold. So we would like to do something essentially the same, but that is frugal enough to be distributed and shared with high school students, maybe set up by a teacher or even set up by some students so that they can explore and observe some of these movements that can be just standard growth or dynamic in response to various stimuli such as temperature, humidity, or light. So the setup that we had started designing, haven't really completed yet, is sort of an optical crescograph. Instead of using the system of levers that involves a couple more moving parts than we necessarily want to involve here, the plan is to essentially use a mirror and a laser pointer, where you have your growing plant here attached to a lever with a counterbalance so you can maintain that at a desired level of tension. You have a mirror there. At some distance away, you have a laser pointer, and really the magnification that can be achieved in this initial setup where we haven't introduced any lenses or further magnifying mirrors that will really increase the power of this system. The magnification that can be achieved is simply the ratio of the sort of output, the bouncing off that mirror to where you're reading it out over the distance of the plant from the axis of the lever there. And you can dramatically increase that just by introducing some lens, for example, that's going to magnify those angles to a degree that we can achieve that same 10,000-fold roughly magnification of plant growth, which if you are basing this off a leaf growing maybe a centimeter in a day, which is a quite reasonable amount, that renders it sensible. You're going to actually see that traveling across a surface of a sheet of paper or something like that. So that's what we've got so far.
Yeah, can you mute yourself real quick?
Sure can.
Thank you, Plant Pulse. I think this is a very interesting revival of the original crust graph using optics instead. I like what the track of like because you're trying to magnify movement. A microscope arguably magnifies things, but this is more or less about the visual and spatial aspect of it and more about just size itself. So using this idea of like a lever or distance to magnify this movement or growth is promising, especially you can make, so that would require a lot of space, but using a lens, like you said, can make the system more compact. One thing that comes to mind right away is like when the signal to noise ratio, like you're going to amplify growth, but you're as the target audience is kids like to poke, like to like touch things and run around, and those kind of vibrations and movements will be amplified as well. So how do you still make it compelling and convincing rather than like they're like, oh, you can't touch it? Because I think the original like Prescott graph was like for a scientific purpose almost. So it's like, oh, don't touch it, leave it alone. So thinking about the robust aspect of it, given the target audience, is another consideration to make. Yeah, any other quick comments or feedback from the audience in the room or on Zoom? Yeah.
What are other things like mentioned growth, movement? Can do that within a day. Like we hope to do growth, we hope to do movement, reactions to different environments. Like what would you guys envision?
Like what might a lesson look
like? Yeah, like a lesson.
Yeah, exactly. And where the sort of plan is to sort of introduce this accompanied by sort of that plan. This is the sort of thing where I choose a particular plant. But the idea might be you can grow whatever you want. But you could have an example lesson plan, just seeing raw growth, having it outside the sun. So you can actually minimize vibrations to a remarkable degree just in the design that was described. I was actually somewhat surprised how much you could minimize those vibrations. It's fine. But to a degree that you could get those benefits. So, but yes, but yeah, designing that lesson.
Yeah. Yeah, it's like when light is on, you see something output. When light is off, the output kind of diminishes. There is one other comment that came to mind. The amount of magnification, I think you'll probably tune this, is based off of, is constrained by over what time scale you want to communicate, which is like, so it's just another thing to help tune your parameters. It's like if it's a 1 hour lesson and you want to show growth over 1 hour, then that will kind of inform your magnification. Yeah. Cool. Let's thank you very much, Plant Pulse. Let's look at the next team. Let's do an electricity-free PCR thermocycler.
Okay, can you hear me? Can you hear me?
Yes.
All right. Well, thanks. Let me share my screen and I can go over the project. This is a very new idea, and we're still in the proof of concept phase, but I like to make posters. And so I'll share my poster that me and my student are working on. Share screen. Okay, let me know when you can see it.
We can see it.
Okay, so the problem that we're trying to address is need for better testing during pandemics and infectious disease testing. So as you all probably know, there are rapid antigen tests that exist, but they're not very sensitive and specific. And the gold standard is polymerase chain reaction, which is a reaction that looks for the viral pathogen DNA or RNA and amplifies it enough times that you can detect it, right? So if you look at the current molecular diagnostic workflow, you have a human sample of an infected patient, could be blood, urine, saliva, sputum. You need to run it through a sample preparation unit where you extract the nucleic acids, the DNA, RNA from everything else. And then you need to amplify a sequence of target that you're looking for. So in this case, it will be the viral pathogen nucleic acid or bacterial pathogen nucleic acid. And this is really one of the bottlenecks because you need to heat and cool the samples 30 times. So the way PCR works is you heat it to 95 degrees Celsius, the sample, the DNA denatures, then you cool it down to 55 degrees Celsius, where primers come in, anneal, and then you move it to 72 degrees Celsius where the single strands become double strands. And so you get from one copy, you get two copies. So it's like a Xerox machine for DNA. And if you do it n number of cycles, you get 2 to the power n copies. So it's a very powerful, exponentially growing way to amplify DNA. And so it is the gold standard. The problem is that these machines, the thermocyclers, are very expensive, $500 to $20,000, and they cost a lot of power. So last year we did this customer discovery where essentially we go and talk to clinicians, healthcare workers, epidemiologists, diagnosticians, and ask them what really was the bottleneck during PCR for PCR testing. Why couldn't we do more testing during the pandemic? And it depends on who you ask. So if you ask these customer segments in developing nations like if you ask them in a developed nations like USA and New Zealand, they basically the need that they have is better sensitivity test. That's their primary objective. But you've asked the same question in places like India and Africa, where some places don't have that infrastructure. Then they say that cost is the main bottleneck and power requirement is the main bottleneck. So that allowed us to look at how we can solve the power requirement aspect, and that itself would drop down the cost as well. So that was the motivation of doing this, and we looked into ways you could do electricity-free molecular diagnostics. So some of you may know this, but this the people have already tried to do centrifugation without a centrifuge. This is from Manu's lab a while back, but they made a paperfuge. It's a toy that you can use to spin things really fast and separate out blood, plasma, and so on. People have also tried to do nucleic acid test without electricity. So this is there's a method called LAMP, which is like PCR, but it's actually not as good as PCR, but it can amplify DNA. And because it requires just one temperature, no thermocycling, you can use exothermic reactions, just chemical reaction that release heat to run this reaction. So no electricity. That was, but no one actually has done this, thermocycling, moving the temperature up and down to do thermocycling. And so before I show you my idea, let me just show you a video and you can possibly guess what's going to happen here. But I'll play the video and I want you to think about what's happening in this video. There's no electricity here, by the way. It's a periodic motion.
Does anyone want to guess real quick what's happening?
Yeah, does anyone want to guess what's happening? Why this is happening? Any ideas? Go ahead.
Noah is talking about cycles of heating and cooling. You can unmute yourself and say it.
Yeah, if you have an idea of what's happening, please, I'd like to hear it.
My guess was just that. My guess was just that, like, as it heats up, it sort of loosens up and just falls back.
Yeah, but why is
But
it?
it seems too like rigid for that to be the case.
Okay, so it's close. So what's happening is there's a permanent magnet here, and there's a magnetic material. It's a ferromagnetic material, and every ferromagnetic material has this property that if you heat it to a temperature, it's called the Curie point of the material. Above that temperature, it loses its magnetic properties, right? So let me show you now with what's happening here step by step. So this is the ferromagnetic material. This is a magnet. So under normal circumstances, they'll be attached because magnetism, magnetic force is strong. But if you keep a flame underneath it, this heats up this material, and it heats up to a point where the temperature goes above the Curie point. At that point, the magnetic force goes down and the gravity force wins. So it detaches. So as it detaches, it starts to cool down because it's not under the flame anymore. So as it cools down, it regains its magnetic properties. And after a sufficient cooling down, it's magnetic again, and magnetic force wins over gravity, and it comes back, gets attracted and sticks to the magnet. And so this cycle can repeat perpetually, like without electricity, right? But also, if you think of the temperature that this metal experiences, hypothetically, it would be something like this. There's some room temperature, it goes up to the Curie point, then it loses magnetic properties, comes down, and then it goes up. So this is a thermal cycle, right? It is heating and cooling the sample or the material without any temperature sensors, right? It has a very fixed point where it detaches. There's no temperature sensor, there's no batteries, there's no electricity, and it can do heating and cooling in a passive manner. And so this 4 stages, then we tried this, like we built a setup where we put a flame, and nickel is cheap. So we just started with nickel. The Curie point of nickel is 350. And so we do see this oscillation. So if you measure, we were able to measure the temperature using a thermal camera. And you can see that temperatures oscillate up and down like a PCR. The problem is that these temperatures are not relevant for PCR. 350 is too high. You want the high temperature to be 95 and the low temperature to be 55. So that then becomes a problem about geometry. We're still doing some tests here, but essentially we can make an alloy. We can make an alloy with a Curie point of 95 so that it oscillates between those two temperatures. So I just thought it would be a cool project to share with you guys, because this is a class where the focus is on frugal science and innovations with simple things. So I think this is a simple idea that can be used to change the way we do thermocycling. So I'll stop there. And if you have any suggestions, comments, and if you want to join the team, please feel free to let me know. So
Loved the idea. Loved the idea. Absolutely brilliant.
thank you.
Yes, very, very clever. I'll make space for anyone else who wants to chime in first. Jackie.
Hey there, super cool idea. I liked it a lot. I wonder, instead of necessarily kind of immediately turning to an alloy or adjusting the temperature of the material doing the pendulum action itself, I mean, could you just rely on the fact that you're going to get a slower rate of heat transfer if you just have a material adjacent to the ferromagnetic material that's actually bouncing back and forth? You might not need to change the material, but you could just have I mean, intuitively, you might do this in a plastic tube where that heat is going to be slowly transferred, and you're not going to necessarily go all the way up to 350 and might stay closer in the 100 Celsius range that you want to keep things here.
Yeah, that's an excellent idea, Jack. So first, when me and my student were discussing this, we thought we'll have to make an alloy, and we looked at the process of making an alloy. It's not very easy.
Yeah.
You melt things. And so my student was the one who had the same idea. Like, why don't we just put an insulator on top, and the temperature over that point will be lower than the Curie point. And when we try that, the response of the thermal mass or change in temperature is not immediate. So you don't get these oscillations. You lose the oscillations. So time scales at which this thing is attaching and detaching is too fast for the thermal temperature to equilibrate over the insulation layer, right? So that would be the first attempt, but it for this time scale, it doesn't work.
Awesome. Yeah, I think yeah, there are degrees of freedom of like, oh, do you want to change the material up, the geometry, the setup? So there's a lot of knobs here. But at the end of the day, when you look at it through the frugal lens, like thinking about distributing it to areas all over the world, like what are things that are immediately available / accessible, and what are ways to have it robust. Yeah, it was interesting that you brought up the lamp amplification thing, because that's like a trade-off between making the reagents more compliant to any environment versus like making or using the traditional PCR reagents with thermocycling, but making the thermocycler itself accessible. So there's a lot of knobs here. Yeah, but it's a very clever idea. Yeah, Danny brought up like what happens if you there's the other parameter is just being further away from the flame.
Yeah.
I think, yeah, that might it also depend, I imagine, on like whether or not the magnet or the paramagnetic thing loses magnetism at 95 sufficiently, but then you can also tune how far it is away from the magnet. So again, there's a lot of tuning.
There's a lot of parameters that you can change to
Yeah.
affect oscillation. And this is a very new system. Nobody has studied this actually. If you look at it, they just know this happens. So we are looking at all the important parameters and actually developing a model, a physics-based model to see
Yeah.
the rate of oscillation and so on.
Yeah. So with all these parameters, it's also good to think about like how do we expect users to set this up in a robust way, is where my mind goes first. Once you do figure out all the parameters that would make this work. Cool. Thank you so much. Let's go to the next team. Let's bounce back to an in-person. How about we do jaundice detection? Yeah.
Okay, cool. Um, yeah, so we're interested in detecting hyperbilirubinemia in newborns and doing it non-invasively for cheaper and locations that are more susceptible to not having the resources to detect it. Cool. I'll give a brief overview of this. It's characterized by elevated levels. So hyperbilirubinemia is characterized by higher levels of bilirubin in the blood. And essentially what happens in newborns is your red blood cells will break down. That produces this chemical. And then typically in a normal functioning liver, that will be processed by the liver. And it converts the unconjugated form to conjugated form, which is then usually peed or excreted out. However, newborns don't have a fully functioning liver, so this can cause a buildup in the bloodstream, which can then affect the brain. And approximately 60% of full-term babies and 80% of premature babies have this. So it's very common, and it's very common that you probably had an excess of this chemical, but eventually after a couple of days, your liver starts to process it, and breastfeeding can also help. Why are most babies born with this? Well, again, typically during pregnancy, it's the placenta of the mother that excretes the bilirubin from the baby. So when the baby is then birthed and out of its environment, its immature liver cannot process it. So another cause of this is breastfeeding failure. So the baby isn't being breastfed, that will dehydrate the baby, and then the baby can no longer excrete, so causing an excess of bilirubin. And then also what I talked about earlier, this is hemolysis can occur, and that's the red blood cell breakdown. And then just general liver dysfunction. So that's an exogenous source.
So some of the symptoms of hyperbilirubinemia is jaundice, which is like just when your skin or eyes look yellow, and that's usually caused by the excess bilirubin in your blood. It like bleeds out into neighboring tissues. And so, I mean, yeah, usually doctors, if they see like the skin looking extra yellow, then, or like the eyes, then they'll send you to get some additional tests. But sometimes the color can be more subtle. And then especially if you have darker pigmentation in your skin, this becomes a lot more difficult to detect. And so this is, even though it normally self-corrects, this is a problem when it's left untreated, because in severe cases of hyperbilirubinemia, usually there's like a 10% mortality, or a even higher chance that you'll have like lifelong comorbidities related to it. And usually these are brain-related dysfunctions. And I think this was a wider scale statistic, but then when we tried to look into more specific mortality rates, like specifically in sub-Saharan Africa or Southern Asia, which is where this is the biggest problem, there isn't really much data available, but we did find several cities in Nigeria reporting mortality rates, and these range from anywhere from 5 to 34%. So I mean, even 5% is alarming considering the amount of cases that we have of this. So there's definitely room for improvement. So the current solutions that we have are like in well built up hospitals would be like HPLC tests, which is basically just a blood test, or there's also a non-invasive method, which is transcutaneous bilirubin measurement. And that basically is just shining different wavelengths into your skin and looking at how much of each of them are returned to. It's kind of like trying to measure the color of your blood without taking a blood sample. But the non-invasive method is not very effective, or not as effective with darker skin, because it relies on light, and darker skin just absorbs more light. And then there's also some less common methods that involve like measuring your blood cell count and stuff like that, but those are not known to be as effective. Should we, or I'll do one more. Okay, yeah. So the current treatments that we have for hyperbilirubin or jaundice is phototherapy, where you put the baby in ultraviolet light and you protect their eyes, and you monitor their bilirubin levels, and this helps break down the bilirubin into the unconjugated form, which makes it water soluble and easy to process. Or exchange transfusion, which is replacing their blood with lower levels of bilirubin levels, and then also breastfeeding. So our problem statement, we found that 1.1 million babies worldwide experience severe neonatal jaundice each year. And the areas where this occurs most are in sub-Saharan Africa and South Asia. And especially because these two areas are areas where people have darker skin, it becomes a lot harder to detect, and it's possible or highly likely that a lot of infant deaths could be caused by jaundice, and it's just not recorded that way because nobody ever knew. And so I think for this condition, early detection is very important because it's caused by a gradual buildup of bilirubin. And so being able to detect it before it's visually a problem, it is definitely an approach that will help us get the best results. So we're trying to develop a device that will help diagnose jaundice early, and hopefully give people more time to act on it to help resolve the condition. Oh, whoops.
Yeah, so putting together our FRDPARRC, we have our we put together functional requirements and such. We have a couple more requirements in this, but we found these 6 to be most important for us. The first one is a for it to be low cost. This is Frugal Science. We're hoping to be more accessible with it. We just did a quick search for existing TCB devices, and most of them cost around $1,000 or more. We were worried about if we were trying to measure TCB in the same way as this device, but significantly cheaper. We were worried about like a more complicated device to use. It may be more complicated, or it may not be as durable, but I think we can leverage different manufacturing techniques to make it cheaper, but still relatively effective. And then our second requirement is that we want it to be effective on dark skin. As Alex mentioned before, jaundice is more prevalent in sub-Saharan Africa, where skin tones are typically darker. And we're hoping to use some kind of like light method, so that would still possibly cause some issues there. And we want to factor that into our design requirements. And some like solution to this that we were trying to think of was like measuring some different parts of the body. So typically measurements for TCB are done on the it was like chest and like forehead or between the eyes. But we can try different parts of the skin, or also the eyes, because jaundice also affects the eyes. We're hoping for it to be a low power device or not use power at all. Originally, we were thinking something with like using a Raspberry Pi, but trying to ideally transition to something that's non-powered, say using sunlight or even just a small LED that will last for a long time with very little battery power, or something that's even like sun powered or anything like that, because again, this is more prevalent in like sub-Saharan Africa. If we check the reference, I'm not gonna actually open it, but we're looking at like percentage of access to electricity in those areas is around only 50%. Also trying to keep it handheld and portable. Just trying to keep it in line with existing devices. And then we want to have it be accurate enough to predict serum levels, and we want it to be accurate to actually be able to be used as a useful test rather than just something that can just be an indicator. And the risk there is that varied skin tone can affect readouts. So again, back to the dark skin tone issue that we're trying to work around. And then the last requirement is that we want it to be made from safe materials, just no lead, especially if we're going to use this on babies. Like, we don't want any chemicals like, you know, coming off of our device and like being even worse long term than would otherwise be.
We're running a lot of time, so that, do you have any more slides, or?
We just have 2 more slides.
Yeah, but that's pretty much, I mean.
Yeah, I mean,
Yeah,
yeah.
I think I want to get to everybody, is there a Notion page that you can direct people to release on them?
Yes.
Yeah, if you can put that in the chat, I think that'd be great.
Okay.
But yeah, I think just quick comments. I think you did a thorough job of defining and understanding the problem. I think the next steps would be to like have some sketches to visualize what form your device will take, would be helpful. But yeah, we'll leave comments on the Notion page. How about next? Can we get passive ocean monitoring? Yeah.
Everyone. So together with Roy and Divya, who Divya can't make it today, we're presenting passive CO2 ocean monitoring. And I'll talk a little bit about why we chose CO2. So current data sets rely on research vessels and what we mentioned like in the start of the class, Argo floats and surface drifters, and they accurately measure water, pressure, temperature, salinity, and other parameters. But one thing that is missing is actually surface CO2 measurements. And there's this atlas. Can you see my mouse? Okay, yeah, there's this atlas which collects all of surface CO2 measurements across the ocean. And in fact, the number of measurements coming in is decreasing as of 2017. First of all, they're very sparse. And as you can see from this map below, these are all the measurements taken in 2023. And in many parts of the ocean, there's 0 measurements taken of surface CO2. And the problem is that these come from very expensive means, such as the research vessels. And of course, increasing levels of CO2, we know why they're important because they give rise to the sea level, disruption of marine ecosystems, and ocean acidification. And so measuring and quantifying the amount of carbon in the ocean is essential. And in fact, there's this cool triangle value chain from this review article, which shows that actually measuring these values leads to policy changes, in the sense that measuring the values, then they go to some atlases that collect the data, and then scientists can map and model some forecasts. And these are implemented in reports, which then lead to policy changes through organizations like the UN. So maybe Roy can talk about by the numbers now.
Yeah, hello. Am I audible? Yes. Yeah, thanks. Gary. So as already Enrico mentioned, kind of like, the numbers are decreasing and the costs are pretty high. So we just try to estimate how high or how much the costs are. That's done by Divya. She's not able to come today. She just got an operation, but yeah, this is her essentially. So if we are trying to do the same thing instead of using, like sensors or something like that manually, how much it would cost? That's the kind of we're trying to migrate.
WOD, can you speak a little louder?
Okay, sure. So we are trying to measure kind of if we do the same sensing manually, how much it would cost us. That's the main idea. So here the assumption is that if we have 10 stations and we have in 7 days we're collecting 10 samples per station. So like that we have tried to, like for each sample, how much time we should spend, the manual labor, the cost of that, and kind of considering everything, the figure is coming around like 1.2 crores or 150K USD, and that's for just 100 samples in a span of 7 days. So, I mean, it gives us an idea of why the numbers are decreasing over the year. If it was, like it's a cost problem also. So that's a kind of rough picture why the need is there to reduce the cost. So next we'll try to understand like what we can do and what is the proposal for dealing with this thing. Enrico, maybe you can shift. So this is just kind of the table we are trying to jot down everything we thought is important. So first thing is like what should be the sensing range? That's the first thing we are talking about here. So it's around 150 to 700, and depending on the seasonal and different geographical locations, this range it varies, the ppm varies. So ideally we want a sensor which should work in this range, and then next is after we have done the sensing and we have collected data, how we can transfer the data to any remote location from where we can access it. So Enrico searched these two platforms. Starlink's is too costly, but ADM satellite this communication is pretty low in cost. And according to some estimation, we have seen that it's possible to at least collect 100 data points over a month. Maybe Enrico, you can focus more on this part because you are the one who found it.
Yeah. So I don't have, yeah, I can go to the link, but there's this really cool chip which integrates well with Arduino and Raspberry Pi, and it does satellite communication from anywhere in the world. It's small, light, low power consumption, and then there's a subscription plan that you would need based on how much data you want to send and receive. And from our estimates, we would need a plan that costs around $20 a month. So of course, this like project we're proposing is frugal in the context of the field, but it's still gonna like we're setting a cap of like $500. We think that could be a feasible estimate. Yeah, and Roy, maybe you want to talk about some of the propulsion mechanisms we were thinking and power.
Yeah, so two things which we feel are kind of like we want to address, like, in a better detail. So one is like the propulsion mechanism, how we are kind of making sure that it can go to different places just passively. So there is a work done by few scientists from JHU. They already have made a prototype similar to the Vela, and also there are other different existing prototypes are there for doing this thing. So that is one aspect of it, but we are also worried about how far it can go. Like maximum time, it has been seen that they are near the beaches. So can it sustain the turbulence if it goes in a deep ocean? Another aspect is also if it gets attacked by, like marine animals, what to do? It's lost. Then the fouling aspect. So if the sensors are there, how long we can actually keep them in the ocean, and we can extract the information properly so that it works fine. And if we want to use a kind of a mechanism to harness the power just from the like ocean, maybe the turbulence, because of the turbulence, if we can convert the mechanical energy into some form of power, or obviously there is wind turbine and solar panels already existing, different models are there, but just a thought if we can do that. That's a kind of the different points we are trying to think. So yeah, if anyone kind of like can shed some more lights on different points or on these ideas, it will be great.
Awesome. I think we'll leave, yeah, if you could direct them to the Notion, yeah, that'd be helpful to leave comments. Also, I think one thing that comes to mind is if you want to narrow in on like setting up the whole platform, or whether you want to focus on a module that will go on an existing platform. I think doing both is like it's needed, but it's also yeah, you could think about long term about which emphasis you want to put on. One thing that comes to mind when setting up a platform, especially that goes on the ocean, is biofouling. And like if a solar panel and salt build up, like there's a lot of headache about what something needs to be in order to withstand like the elements of nature. Yeah, but great Fred. Yeah, and analysis of yeah.
No, yeah. So this CO2 sensor, there's a lab on Stanford who's developing a low-cost solution. So we were hoping to collaborate with them, but like there's lots of technical details to iron out on that side. And so in terms of feasibility for our project timeline that we have in this class, I think, yeah, you're right. It would be interesting to focus on the platform itself and then integrate that sensor and work with those people. Yeah.
Again, I don't think you had again, I know there's a time pressure for the course, but like this is a real world thing that can work. So you should think of this as not like, oh, how can I wrap this up in like 2-3 weeks? It's like, how can this set me up for success, or like so that I can pursue it or hand it off to so yeah, don't let the 2 or 3 weeks impede your longevity thinking. Yeah. Yeah. Okay.
What's expected?
I think at the very least, I want to see something physical. Yes, it doesn't have to be as polished as Foldscopes, but I think taking that leap of faith to make a prototype and have something physical and synthesize everything that you've learned is like that first step is a great leap, I would say. And that will kind of set the momentum for however far that you're able to take it. But yeah, something physical. Next, I guess we have two more. So yeah, can we have the mosquito surveillance?
Okay, so hello everyone. We're the mosquito-borne disease prediction group. I'm Ragat, and these are my teammates. So go. Sorry, one sec. Let me try to be sharing. Oh, just click on it's trying to ask.
Yeah, there we go.
Okay, there we go. So first, let's talk about why it's a problem. So this is by the numbers that I shared briefly during class, but we can talk about it more in depth here. There's about 110 trillion mosquitoes in the world during high season. And just for context, that's about the mass of 15,000 blue whales, which is crazy. And 50% of those are able to feed on human blood, which would be the females, which would be about 50 trillion mosquitoes. And to sustain themselves, they have to bite every few days, which here we're estimating is 72 hours. So if you crunch the numbers, that comes out to about 193 million bites per second. And so there's a huge risk factor here regarding human health because they spread a large number of diseases. So there's 2 or 3 key vectors that we can talk about. First is the Aedes aegypti and the Aedes albopictus. They both carry the same diseases, with the aegypti being the primary vector and the albopictus being the secondary. So the diseases that they carry are Zika, dengue, and chikungunya, all of which have different symptoms, different morbidities and mortalities. Zika is particularly known for causing a lot of problems with pregnant women and disabilities in unborn fetuses. And both of these are unique in that they exhibit large migration and increase their spread over the years as climate changes. So both have been shown to expand their habitat a lot. For instance, the albopictus has spread 93 miles per year in Europe in the past 5 years compared to before the past 5 years where it was only about 63. So we're seeing a large increase, which most scientists predict is driven by climate change and increased human travel. And then there's obviously Anopheles too, which is the malaria vector. The concern with it is that it exhibits motility between rural and urban areas. So as we know, there's the Stephensi Anopheles that is becoming more and more prevalent in urban high dense populations, but it doesn't exhibit as much global motility as the Aedes mosquitoes. So this is a very interesting study that projects from 2019 that projects the prevalence of the aegypti and the albopictus mosquitoes to 2050 based off of climate and human travel. So here it presents 2 different kinds of habitat for the mosquitoes. The first is what's called the natural ecological habitat, which are habitats that are currently already suitable for the mosquitoes to be in. And so the prediction is that by 2020, this paper was published in 2019, by 2020, the aegypti would have already saturated its naturally occurring ecological habitats, again, driven by human migration, and the albopictus by 2050. And so past that point, their movement into new habitats is mostly going to be driven by climate change, creating new habitats so that they can move to. So if you look at these maps, the first one here being the aegypti in 2050 and the second one being the albopictus in 2050, you can see that there's very large coverage and also very large increased coverage. So you can see that the Aegypti, for instance, here doesn't cover this part, but the Albopictus does. And so their combined geographical concentration is very concerning.
So let's just get into the present human burden, because talking about the number of mosquitoes sometimes doesn't make us understand what the real impact is on people around here. So about half the world's population now live in dengue risk areas with an estimated 100 to 400 million infections and up to 36,000 deaths each year. I've had dengue, not fun, don't recommend it. And I was lucky enough to have access to good healthcare, but most of the people who end up suffering from these diseases live in peri-urban or rural areas, so they oftentimes struggle to even get healthcare for such a debilitating disease. In addition, in 2022, there were 249 million malaria cases and 608,000 deaths, but almost all of these deaths were in low and middle income countries, despite half the global population being at risk. Starting to see a bit of a pattern here. And in 2023, we did have $4.3 billion available to fight malaria. That sounds great, till you realize the WHO thought that we needed another $4 billion. And this present human burden covers only 2 of the 300 plus diseases that mosquitoes can transmit. As Raghav was mentioning, there's Zika, Chikungunya, and others that are equally debilitating and affect different populations. And so what are the challenges with surveillance? Let's just talk about that. First of all, constrained budget and lots to do. There's a few countries that are particularly affected by malaria that have national malaria strategic plans. And electronic mosquito surveillance typically takes up about 0.5 to 1.5 of that budget, or generally between 7 to 21% of surveillance budgets in general. That much of a budget has to look at data collection, reporting infrastructure, and analysis to healthcare providers, policymakers, etc. That just is insufficient given the stakes of the problem we're dealing with. Another huge problem is high per unit costs. In West Nile virus surveillance systems, the average cost per mosquito trap is about $72 per week per unit. Think about countries that bear a lot of these burdens that have to deal with mosquitoes, like Nigeria, other countries in sub-Saharan Africa. I just checked the currency conversion rate for $1 there is 1,600 in the local currency. And this is charging $72 a week per unit. This is not even taking into consideration the cost of delivering these traps to the people that need them the most, the construction of these traps, and managing the data you get from collecting the mosquitoes in these traps. And it gets even worse because we have a lot of data blind spots in countries like Burkina Faso, Cote d'Ivoire, Zambia, and other countries in sub-Saharan Africa. Because of budget shortfalls, governments have decided to suspend or close routine sentinel surveillance sites, which means we don't even know the extent of the problem in some of these places. So, very simply, climate change plus existing mosquito surveillance challenges is really, really bad. So what are we going to do about it?
Yeah, and so yeah, this is our FRDPARRC table. I can go through like some of the key things because we don't know exactly what our solution like precisely is going to look like, but we've like floated around a few different vague ideas. But yeah, but in general, like functional requirements, we want it to be low cost and just help with like general monitoring of different mosquito species to help with like prediction of the migration and like disease prevalence and things like that. So like any predictions of like infection probability, we want them to be region and temporally specific. Yeah, and then depending on what exactly the solution looks like, we've kind of floated the idea of since there needs to be like some kind of physical aspect, maybe thinking about mosquito classification because different species carry these different diseases, and we could focus on some of the more dangerous species that Raghav had talked about a little bit earlier. So like mosquito detection and like species classification could be really useful. Whatever this device is should be durable, store and transmit data that can actually lead to kind of actionable outcomes. Simple to deploy, it would just be ideal, especially if like everyday people could kind of help facilitate the use of this technology. and scalable use / manufacturing, depending on like what the solution is exactly. So yeah, we design parameters. We'd like to use some existing. We're like looking into using like existing data that's out there, like existing surveillance methods. From our research, we found some different ways of classifying mosquitoes, being like visual classification. So like a lot of the time, and to like insect scientists, we'll just like look at the mosquitoes and just like identify the species from there. But there's also technologies out there that use like acoustic detection by looking at the frequency of like the wing beats and things like that to identify mosquitoes. Other like general ideas, maybe like a passive trap to trap mosquitoes and then using that to sample like the species somehow. It would be nice if it was battery or solar powered, not using too much electricity, so it could be used in a lot of these rural areas that don't have a lot of existing infrastructure to implement these things. An app to make visualizing like any predictions like more easy to use and useful. Yeah, I think some of the references that we've looked at, our Humbug is like a smartphone like app that that's kind of the acoustic detection that we talked about, where it identifies mosquitoes based on just like audio, like listening to them. And then there was also this paper that talked about a low-cost imaging system that they developed, where I think the general idea was that they trapped mosquitoes and then the system like took images of the mosquitoes and then sent them to actual like scientists to like manually classify the species. But it would be nice if we could do something that was like maybe like using machine learning or like something like that to just like automatically like use the technology to like automatically classify the mosquitoes. And then another source about like these vectors that we talked about and their migration patterns and how that's becoming a big threat. But yeah, those are like general ideas. I know we're low on time, so we can stop there.
All right. Thank you, mosquito surveillance team. Quick comment. I think again, we can flesh this out a bit more, but in terms of narrowing in on a solution, the passive trapping and identification is most in line in my head with surveillance. Like expecting people to like go around with apps. Like I think, although like phones are very prevalent nowadays, like I think it's also important to consider the amount of time and labor you expect people to be doing given their busy schedules already, right? So a passive trapping and identification thing, if you can narrow in on like that sort of technology, I think that's promising in my head at least. And we can pick Manu's brain on that and other folks in the class, but I think this is a thorough FRDPARRC table and promising start. So good job. Cool. I think. Yeah, I think that you're the last group.
I can go.
Yeah. So let's have Coral Helping Hands go right now. I know it's almost the top of the hour if people need to go, but otherwise yeah, let's wrap. Yeah. Yes.
Okay, also, Debbie and WNG are.
I think you had to unmute your audio.
How do I turn my one? Debbie and Devianchi are both sick and recovering, so wishing them well, and I think they'll be here on Monday. But so the project we've got, our crew is Helping Hands Coral Bleaching Recovery. You've heard us talk about it before. How do I? Oh, there we go. But just reiterate, coral reefs are one of the most important ecosystems in the world, which kind of goes without saying. But what people don't always appreciate is they take up just 0.1% of the ocean, yet they account for over 30% of known species. So these little pinpricks that are just really oases of life, and they're undergoing coral bleaching, which is where they're turning white. One of the largest ecological disasters facing the Earth today. Corals can bleach under many conditions. If the water gets too cold, if there's too much light, too little light, disease, acidification, but primarily when the water gets too hot. when it's too warm. And it can happen one of two ways. One, if it gets too hot for just a couple of days, or if it's too warm for too long. And you've heard us talk about these symbionts. So these symbionts, I think it's always great to have visuals. You can see in the bottom right corner. These are single-celled algae that are living in the coral's tissues that provide over 90% of the nutrients. So they're vital for the coral survival. When the water gets too hot, these algae produce toxins that the coral doesn't like, and they kick out the algae and turn white, starve, and then die. A lot of work is looking at how do we prevent this from happening? How do you prevent the algae from producing toxins? How do you prevent the coral from kicking out these algae? But not many people are looking at this little window. How do we get the symbionts back into the coral and recover them? Another thing is also everyone kind of treats bleached corals as dead, but a white coral is not dead yet. It's this little kind of operation where we can try to sort of keep them alive. Another thing of great visuals, which is important to understand, is the experimental setup right now at Hopkins of the things that our group is working on. We're working with coral. The specific coral is Poeciloptera damicornis, which is called cauliflower coral. It's non-native from the Indo-Pacific, so we have to have special tanks to make sure that we don't send the larvae back out into Monterey Bay. Possible for invasive species. They couldn't survive in that temperature, but still it's important to treat them as if they could be an invasive species. This project is based around this idea of it's simple but not necessarily intuitive. Can we recover bleached corals by just touching them next to healthy corals? And so you can see the top left corner. Literally, you just fragment these little pieces, and we're gluing them and just touching them next to each other. And the control is we put them just a couple of millimeters apart. And we've got multiple ongoing experiments with multiple replicates and concurrent getting results. And shown here, just to show just the kind of stark contrast between a bleached coral that doesn't have symbionts, very white, versus you can see in the background the healthy coral with all those symbionts and those color and nutrients. Of the bleached corals that aren't touching, again, just a couple millimeters apart, we've have 0 signs of recovery over 28 days, 35 days, and multiple weeks moving forward. They're losing tissue and they're dying. And obviously that's not ideal, but it's interesting to show that just being so close to a healthy coral but not touching it, there's no signs of recovery. But shown here are the ones that are touching. The symbionts at that interface seem to be traveling over and recovering the bleached corals. And so you can see here, this is just a kind of progression photo over just a handful of weeks. We can show that we can actually recover a bleached coral and make it into a healthy coral, which is really exciting. We've got multiple different these fragments that are recovering in just a short time frame. By the numbers that Devyanshi and myself both did, I had mentioned about we tried to calculate how many symbionts there are in the world. And what was really cool is we independently did by the numbers. We used different methods, and we both got roughly 10 to the 20 number of symbionts in the world. You can see zoomed in here just how small these symbionts are. They're just a handful of microns. The little teeny pinpricks are right next to those polyps there. And to put in perspective of how large of a number 10 to the 20 is, I did some other fun calculations, and there's more symbionts than grains of sand on Earth. There's more symbionts than permutations of a 3x3 normal Rubik's Cube. More symbionts than seconds since the Big Bang. And more symbionts than possible YouTube URL combinations, given their current 11-character system. And the crazy actually is there's more symbionts than all 4 of these combined. So you can combine all 4 of those numbers, and that's still more than 10 to the 20. Another fun little calculation is that, again, these are just very small microns. And if you line up 10 to the 20 symbionts end to end, how far do they stretch? I was curious, would they wrap around the Earth? Would they make it to the moon, to the sun? Does anyone have any guesses of how far 10 to 20 symbionts would go? There's a hint in there, but it's not obvious. The sun? Actually, it's, yeah, they're microns. Yeah. Yeah. So it's actually a light year. So it's 10 to 15, it's 10 microns, so it's 10 to the 15, but it's actually like a light year. So if you stack them up, it's a light year of distance, which is kind of crazy. And for reference, light goes around the sun, can go around the Earth 7 times every single second. So every single second for a full year, 7 times around the Earth. Add that all up, that's as many symbionts we have on the Earth, which is kind of crazy. And then lastly, last little fun, the numbers that we did was symbionts are living organisms. And so they're an underappreciated carbon sink. And so we tried to calculating the biomass of these symbionts. There's not great data on how much a single symbiont weighs. So I found the weight of a E. coli assuming roughly similar densities, then calculate how much E. coli would fit into a single symbiont, and then calculate the densities up from there. We had slightly different numbers, but seems roughly that they could sequester upwards of 10 to the 5 metric tons, so 100,000 plus metric tons, which is upwards of the carbon emissions of numerous countries on the smaller end of those smaller countries. And actually, I don't know, we got to double check this, but roughly the exact same amount as the amount of carbon produced by Palo Alto last year, which is over 100,000 metric tons of CO2. And then, so for our frugal goal, we were talking with Manu, and he wanted us to go for 100 times the possible problem we could tackle for 100th of the cost, which is pretty daunting to think about. A number that we landed on, which again is a really kind of difficult for us to wrap our head around, but a good reach goal, is we would want to try to recover the amount of area of a football field or soccer field, football, however you want to think about it, for just $100. So a football field area of coral for $100. We'd heard us mention that the number world's coral kind of is up towards the size of Germany, and there's roughly you could fit 65 million football fields in the size of Germany. So that kind of puts to solving the world's coral problem at $6.5 billion, which again is a huge, huge number, but in the grand scheme of things, it's reasonable. And then to get to a football field, that's obviously a huge amount of area to cover. So that's definitely a reach goal if we were to scale up, but still one to kind of think about and easy to kind of comprehend in the size scale. We'll go over this really briefly, but the underlying mechanism of how these symbionts are traveling into the bleached corals from the healthy corals, we're still not entirely sure of how that's happening. Coral as an organism in its biology is really, really wild. As you see the left photo, out of the water, you can see this little kind of black holes on the coral, and those are actually individual polyps. So coral's a real weird organism. It's colonial. So each of those individual polyps is an animal that they can asexually reproduce, so they can turn one polyp into two, and they grow themselves. They can also sexually reproduce. But each individual is an animal, but they're all connected through tissues. So the symbionts are actually living also underwater. When you see that actually under the water, they all the polyps come out, and so you can actually, it's very much of a living organism. People kind of think them as rocks, and almost as you can see on the left side, but under the right side, you can see they're really a living and dynamic organism. The symbionts are kind of living in the tissues of individual cells of the coral. So the question is are they traveling across and kind of getting into the tissues, or is it just from the symbionts being spit out from the live corals? So those are some questions we need to answer. Other things, running out of time, I think, but Debbie, who does a lot of work in the 3D bioprinting space, we initially were really excited to kind of get into 3D bioprinting, but Manu challenged us to think of more solutions. So we sat down, Debbie and I, and I had the slides wrong, but and we were thinking about beyond just the 3D bioprinting, it's also important for the immediate response. And so we want to think of ourselves as emergency services, and beyond just getting the symbionts to the corals, we also want to make them stable. And so there's two main ways beyond including the symbionts we have to worry about is getting them food. So I'd mentioned that the symbionts provide 90% of the nutrients, but that means they can get 10% of their nutrients elsewhere. And so that's actually because these polyps are grabbing things out of the water. So they're grabbing plankton, they're grabbing nutrients out of the water for themselves. And so when they're bleached, it's important to feed them to keep them alive long enough to possibly recover the symbionts. And then the one in this photo right here, it might look like the coral's actually recovering, but this is one of the ones that's not touching a healthy coral, and that's actually overgrowth and the coral dying. So that's not bleached recovery. That's not recovery. That's actually death. And so beyond just feeding them, we also want to make sure we protect them against overgrowth and possible disease. And so with that in mind, we also challenged ourselves and we came up with a number of possible different solutions beyond just the 3D bioprinting. We're still really excited about the 3D bioprinting, but I'll just briefly walk through some of these solutions. Top left is, could we grow them in liquid culture? And could there be high enough concentrations that we could just dump them into the water? You worry about diffusion, that's not a good friend, but be curious if, are there high enough concentrations that they could just get into the coral? If we grow them in liquid culture, could we also have a sponge? We have a sponge that we soak them up, soak up the symbionts and place out in the coral and diffuses out. This is kind of a hydrogel mucus. So corals have a bunch of mucus. So could we have some synthetic mucus that we put into them? Because the symbionts are living in the tissues, these are actually microneedles. So is there a chance that we, instead of waiting for the corals to uptake the symbionts, this is a fun one, could we just inject the symbionts right into the tissues and have almost an immediate recovery? That's unsure. Kind of one of the crazier ones that I really like. I think it's kind of out there, but there's these things called coral dwelling crabs that kind of burrow in the skeleton of the corals and live within the corals and the tissues all around them. And so could we kind of pollinate these crabs and load them up with symbionts like bees, like they have pollen, and then have the crabs go into the corals and then recover them as they sit in their dwellings. And could we have them recover them? We also we looked at 3D bioprinting. Another one's exciting. These are Orbeez, which are kind of gel beads. I don't know if people are familiar with those, but could we have Corbeez where we put the symbionts in these Orbeez and place them out? If the coral needs to be alive, could we just take individual polyps and put the polyps onto the coral and then have it kind of grow out venom style from that individual polyp? We also had mentioned biofouling. Could we grab some rope that's biodegradable? We could biofoul. And then lastly, given that these are symbionts, they're in the marine space, they're actually not viewed as part of the coral microbiome, which is interesting. But it's interesting to think of that. Could this be viewed as a human microbiome problem, and think of the corals that they just got hit with antibiotics, and could we provide them with probiotics? And so could we think of some pill delivery? And then lastly, we have some field deployment. Could we do this with humans? Could we do this with remote operated vehicles? There's some great soft robot work done at Stanford, or possibly with nets, of picking one of our 10 different solutions and applying them with multiple different ways of how do we get this into the field for a low cost, rapid solution.
Naturally find like a host for.
So there's two ways. One, like they actually can, like there's vertical and horizontal transmission. They can also just from the larvae that are given off through asexual for sexual reproduction, the symbiont's already there. But also Manu in his work, actually, they're looking at somehow the coral are able to interact with the symbionts as they're in a larval stage. And when they're larval, the coral actually can swim around, get really weird biology, get the symbionts, and then they'll settle, and then they'll begin to grow with the symbionts there.
Cool. Yeah, and if people want to leave comments, can you direct them to Notion pages so that we can get all the feedback we can. I've recorded this, so Manu will watch this afterwards and give his comments and feedback. In the meantime, like, great job, everybody. I think this is a great start. The next step is to try to start making those ideas physical. You have to start somewhere. So it can start with a drawing, but then start putting scrapping pieces together to start visualizing and iterating on the idea. Don't try to have like a perfect start. I think any start is already great, and then it's about iterating afterwards. Okay, cool. I'm gonna end the recording now.